Okay, welcome everybody to the CephFS and Samba session. I have David Disseldorp here with me. My name is Jan. Yeah, let's dive right into it. In case you want to grab the slides right away, feel free to follow along on your device if necessary. Otherwise, I think we have pretty good projectors here, so that should be fine. Seeing a few phones. Probably mostly testing if it actually works. All right. I'll show it again at the end, so don't worry if you couldn't grab it yet. All right, our agenda. Actually, can you make that a little bigger? We'll give a quick intro to Ceph and CephFS. I think most of you here should be familiar with the software components, but just to catch everybody up. Then I'll highlight a few of CephFS's new features that we'll get with Nautilus and with the upcoming SES6 release. David will take over then and talk about the Samba Gateway and all the nice things you can do there. And then we'll actually have some performance numbers, essentially fresh, hot off the machines, like literally 20 minutes ago. So. We can have a little analyzing session with all of you here, but we didn't want to keep those numbers from you. All right, then let's get to it, I guess. So yeah, Ceph, I guess everybody has heard of that by now, is a distributed storage system based on the Rados object store. It originates from a research project now quite a while ago. I believe over 10 years ago, it was first mentioned in a research paper. It is scalable by design based on this Rados implementation. It is fault tolerant and it is self-managing and self-healing in most cases at least. So this is quite nice. And the big selling point of Ceph is, of course, the unified storage cluster where you get block, object, and file storage all in one system. Maybe let's look at the architecture a little more in detail. As I mentioned, we have Rados as the basis. It is a object storage system, which is based on the Crush algorithm. Crush implements something that is called rendezvous hashing. I always thought it's consistent hashing, but I learned differently in the preparation for this presentation. And this really provides the reliability and high availability and self-management features that Ceph has to offer. All this is neatly wrapped in a library in librados, and on top of those we have all the nice access mechanisms that everybody uses. And of course, we'll be concentrating on CephFS today. Just a few words about CephFS itself. So a basic Ceph cluster consists of two daemon types, the OSD and monitor daemons. The monitor daemons keep cluster state for you and keep it globally consistent. And the OSDs are there for storing your actual data. For CephFS, then we add another daemon into this mix, the MDS Demons. And yeah, for file, we need metadata. And while this metadata is still stored in Ceph, so in Rados itself, so the metadata of the files is reliable and high available and everything, we do need a daemon or a set of daemons that manage the access to this metadata. And that's exactly what the MDS Demons do. I like to say they're actually only a cache for the metadata pool, but they do a bit more, so they're very sophisticated caches. Nevertheless, they are stateless, so they do rely on the data that is stored in Ceph itself. Yeah. Oh, and one thing to mention here that is really neat is that any CephFS client, while it will talk to the MDS daemons for metadata, they will speak directly to the OSDs to exchange data, which really scales quite well because you know, if they access a lot of data, they can talk to a lot of OSD daemons in parallel. Okay, so much for an introduction. Any questions so far? I think this should be knowledge that everybody had before they came here. Doesn't look like it. So yeah, let's get to some more interesting stuff. So CephFS, we didn't have CephFS for quite a while, and it's still quite new. So with Dual, CephFS was declared production ready, which some people considered a stretch, but by now with SES 5.5 we are shipping Luminous, so it's quite mature, and with Nautilus obviously stability is quite improving, and we're getting quite a nice bunch of new features, and I just want to highlight a few here. So multi-MDS Demons is a feature that arrived before Nautilus, but is really starting to come into its own. I showed the architecture slide, and of course I mentioned that you need an MDS for your file system, and that immediately brings up the issue of what if your MDS fails. Of course, if you only have one MDS and that fails, that will bring down your CephFS instance, which is less than ideal. Or if you have very, very busy CephFS instances, a single MDS might get overwhelmed. You know, think of a working set of a few million files or so. One MDS will be quite busy with that. So CephFS supports multiple MDS daemons. By default, you can simply start a new CephFS daemon. It will start talking to the cluster, and it will join the cluster as a standby daemon, or actually as a passive daemon. So whenever the active MDS, which you should have one of at least, obviously, in case that goes down, the passive MDS will replay the log of the old MDS and will take over for that one. We'll talk about some options for that in a minute. So this covers the high availability issue, but we also want to be scalable. So for a given CephFS instance, you can set an option called max MDS. So if you want multiple active MDS daemons, you simply set this option on your CephFS instance with, you know, the name CephFS is quite common. And the daemon that we've just started up here will then join as an active daemon, and they will actually partition the directory tree that you have in your CephFS between them fully automatically and based on load. Yeah, so this covers, you know, high availability, scalability. Of course, you always want to combine those two approaches. In fact, Ceph will complain if you don't have at least one standby MDS daemon. It will give you a warning because it just considers this a necessary requirement. Yeah, I mentioned that this is actually fully automatic, but there's quite a few options that govern the failover handling as well as this partitioning. The failover parameters, they have very sane defaults, but for some deployments it might make sense to play with them a little. So the MDS beacon grace time is, of course, the time a standby MDS will wait for an active MDS to ping back. If you have, you know, a CephFS file system that needs to be very highly available without long interruptions, you want to reduce the default of 30 seconds a little bit. That, of course, requires a network in your data center that you know, rarely has gaps that long because you don't want an MDS falsely being marked out. I mentioned standby already. You can configure standby daemons as a hot standby where they constantly will keep up to date on the metadata operations that the active MDSs do, so it can take over immediately. Of course, that increases the load on the standby MDSs a little bit, but it's just a sane feature to enable by default. And then you can to configure certain MDS daemons to stand by only for specific active MDSs, but that is gets already into very involved setups, which yeah, I don't see all that often in the wild. The partitioning can be controlled as well. I started talking about ranks here. So this partitioning of the directory tree, that is called ranking. So they're partitioned into ranks. And one active MDS will simply take over for a rank. This is just a distinction that is being made so that you know, the MDS daemons are fairly independent and they can serve any rank. And to make this distinction clear, this phrasing is used usually. Yeah, as I said, there's experiments that upstream has done. It is really, really hard to beat the automatic partitioning, which is based on the hotness of a directory. Nevertheless, there are some options that govern that, and this might make sense. So if you just want an equally loaded MDS daemons, you shouldn't touch those, but it might make sense, you know, if you want to, for example, have a directory that gets very bursty traffic. It might make sense to pin this directory as a rank to a certain MDS. That when this job in this directory suddenly happens and, you know, gets a high I/O load, it doesn't impact the rest of your file system. So it's kind of a fencing mechanism. Right, and I haven't shown you yet how to do this because this is on the next slide. This directory pinning all happens via extended attributes. And there are actually quite a few behaviors in CephFS that can be governed by extended attributes. The interface here is really what you would expect from extended attributes. I think most of you have seen these setFattrib and getFattrib calls. To delete, you just use the -x option. And down below here, I try to kind of condense the configuration space that the extended attributes offer. So these are the names of the extended attributes. The top one I mentioned on the slide before is the directory pinning. And yeah, you just, as a value, you just give it a rank number. So say you have a directory that, you know, gets once an hour, gets a high I/O load. So you would just activate an MDS for it, say there would be rank 2, and you would just pin this one directory to rank 2, and that would keep all your other directories in your CephFS fenced off from this high I/O load. Quotas are being set with extended attributes as well, and file and directory layouts, which are also quite interesting. But I don't really want to get into it very detailed here because yeah, there's a lot of stuff you can do. So you can add, for example, a second data pool to CephFS. For example, you have, you know, a pool with spinners. You create another pool that you define a crush rule for, so they end up on NVMe drives, for example. And then you can have one directory in your CephFS instance that is only stored on the NVMe pool, making it very fast. There's a lot of stuff that can be done with that. There are some caveats that I need to mention. So especially the layouts, these are inherited by files and directories under a directory where this is set at creation time. So if you set a layout extended attribute when you already have data in them, it doesn't apply to this existing data. It only applies to new data. And that can be a little confusing. Same goes for quotas, by the way, I think. And just to mention, for those of you who actually, you know, have a deployment, you know what CephX keys are. If you want a client that is able to manipulate these extended attributes, it needs the P flag. And I'll have an example later on. Oh yeah, and one thing to mention too is that some extended attributes need some prior actions before you can actually do anything with them. Again, I mentioned the file layout pool. If you only have one pool in your CephFS instance, there is no point in trying to set a different pool because there is none. So you have to add another data pool to your CephFS instance first before you can actually do anything with this extended attribute. But I think that shouldn't be so surprising. Quotas. My quota slide was very short. They are directory based and they're configured with extended attributes. And then I needed some more things to say about quotas, and there are quite a few limitations. Yeah, quotas in a distributed system are very hard. So the current implementation is a first approach, and there is actually a PR open right now that implements user and group-based quotas, which is heavily discussed. So there is some development there. But yeah, basically the quotas need cooperation from the client. So if you have a malicious client, they can just ignore the quota settings because these limitations are adhered to in the client, not in the servers. They're imprecise, so they periodically, the client and the MDS exchange these quota information. So it is possible for a client to go a little bit over. The kernel support is quite recent, and I mentioned those layout extended attributes. Sorry, no, that's wrong. In CephX, you can also implement some restrictions on which kind of path a client is able to see that can interfere subtly with quota settings. So yeah, you'll need to read up on that if you want to implement quotas, but they're there. And of course, the feature that everybody was waiting for is snapshots landed finally. Again, a very short slide for a very, very complex feature. So snapshots in CephFS are directory based. So you can snapshot a directory and everything that's under it. Very easy to create a snapshot. It's just make dir on a magic directory, and it's very fast too. Yeah, and listing and removing them is just as easy. I don't know what else to tell you, other than that the implementation is insanely complex. Again, another caveat here for the CephX keys, you need the S flag set so user can actually create snapshots. Was there a question somewhere? No. Yeah, and I think we'll see some nice features in the future with that are based on snapshots. I mean, so far it's a fairly naked feature, if you will, but I think there's going to be some work being done on top of this in the future, which I'm quite looking forward to. Oh yeah, this is the CephX example that I mentioned. So you'll see in the MDS capabilities, you see this S back here. This is exactly this S flag I was talking about. So this client 0 user would be allowed to create snapshots. And if the S would be a P, same story, just for quotas. And with that, I talked way too long already. I hand over to David.
Jan?
Just a question.
Oh, sorry.
I have a question. When you are talking about two MDS that are acting at the very same time, I mean, that implies that you need a third MDS in order to have full recovery in case of failure?
In order to have a healthy cluster, yes, Ceph wants a third passive MDS.
N plus 1?
Yes. Well, otherwise Ceph will create a health warning. I believe there is a setting somewhere where you can just turn off that warning, but I mean, it's there for a reason.
No, well, but that implies even that, I mean, because somewhat confused, maybe we can get a little bit offline, but anyway, if the standby MDS, I suppose that is listening to everything that is happening on the other two guys, that means that you have some over provisioning on top of that guy in order to be able to listen to both. It's doing twice the job at the end.
Well, no, I mean, this is all, there is a log structure in place where the operations get, appended, and it just keeps an eye on that. It doesn't actually follow the data or the metadata operations, because the metadata lands in the CephFS metadata pool anyway. So that's what I meant in the beginning, that the MDS Demons, they're stateless themselves. So they don't need to hand over any state. A new MDS can simply look in the metadata pool and get the necessary information.
Okay. I'm David Disseldorp, so I'll just start off with sort of some features or integration work we're doing with CephFS in Samba. So this is sort of all ongoing in the lead up to the next SUSE Enterprise Storage 6 release. And I've just switched off. There we go.
Go left and right.
Yeah, I don't trust it.
Okay.
So just a brief introduction to Samba. Basically, if you have a router at home, you've probably already got a deployment. It's just a file server that speaks SMB. SMB is then used now by Windows. Apple clients are by default nowadays too, and there are also then Linux implementations. So the kernel client is a main one. It handles integration with Active Directory too, so you can do authentication, ID mapping on your Samba server between Windows and Linux users and groups. Within Samba we have a gateway for CephFS. The gateway itself is sort of implemented as a back end for Samba. So Samba has a pluggable VFS layer. And there we have then sort of integration with libCephFS, and this then handles sort of the mapping of these SMB client requests coming into then Ceph OSD requests to the back-end Ceph cluster. We support one or more gateway nodes, so obviously with a highly scalable, reliable Ceph backend, it makes sense to have some sort of redundancy with the SMB servers in front. So we do support that. Here's just sort of a basic diagram of the standalone Samba Gateway case. So we have, as I mentioned, the libCephFS sort of providing the integration or I/O path to the Ceph cluster. Otherwise, the SMB protocol implementation is then handled by Samba. Important on the right is that we have this TDB component. So that then handles basically the state storage that's needed with the SMB server. So things like open files and locks. We have to then have some sort of database or key value store to retain that state. In the clustered case, or for this state storage as well as other things like reliable messaging, we have CTDB. So CTDB is, I guess you could say, an evolution of this standalone TDB database, in that it then gives us, to some degree, scale out, clustered Samba serving. It has some HA features in there too, so it can do things like IP failover and also ensure that specific services within your cluster are up and running. CTDB itself, so it also does, similar to Ceph, basically calculated placement for records within the database. So you have what's called a location master and a data master. So if you're interacting with a record, you can then determine who to ask for that record, and then from there you can determine where it actually resides within the cluster. We have a single, or within the cluster, a single recovery master. So that basically then, in the case of node failure, handles failover and recovery of any databases mid-transaction, whatever's needed. Yeah, for that we also need a cluster-wide mutex just to avoid any chance of split brain. So for that cluster mutex, we've also done some work on integrating with Ceph, so using Rados locks to provide this mutex instead of or something we've used in the past, which was DLM, so a separate distributed lock manager. I think I mentioned that earlier. So it handles IP failover, and within CTDB itself, it also tracks then the clients that are connected, and it basically has this special ticker-lack functionality to basically, once IP failover occurs, it then forces a quick TCP session reconnect or reset, on the client, just to speed up failover there. So this is then a diagram of the clustered case. I'm still just looking at a single clustered Samba node. Again, we have just the regular VFS Ceph backend for Samba, but instead of TDB, we have this separate CTDB daemon, which is then handling our clustered key value state storage. At this stage, it's, or at least within SUSE Enterprise Storage, it's a new feature. So we had it in tech preview with SES 5. With SES 5.5, we then went to full support, but we do still have some limitations in the existing implementation. So we don't currently support cross-protocol access, so you can't share something through NFS and the Samba Gateway. Performance isn't great. You'll see some more details on performance soon. We don't support leases, which is then basically giving the SME clients sort of the ability to do some smart caching locally. Node failover isn't ideal. This is more sort of a problem within the SMB protocol itself, which is to some degree been improved in recent SMB dialects. So I mentioned earlier we have this IP failover, and we're then resetting the connection on the client. That obviously has an impact on the application. It forces the application to then reopen and restart I/O. So with recent SMB dialects, we have this new SMB witness feature with persistent handles. That then, of course, talking about sort of the future when we get to having this sort of support, we could then offer much smoother failover between nodes. Load balancing too. At the moment you can do things like just round robin DNS, but again with witness we can sort of then tell clients which gateways they should then connect through. So now on to a demo. I guess I should mention beforehand that it's just so this is all pre-release SES 6 code just running on my laptop locally. So there's a good chance it'll go up in flames, but let's see what happens. So first off, just hope to show the basic CephFS snapshot implementation, or usage, sorry. So here, is that large enough? Yeah, looks okay. So I've just got an empty CephFS file system mounted locally on this VM. And within that, I was just going to create some data beforehand. So we've got some data for the snapshots. Also create a directory. And so Jan mentioned earlier that snapshots within CephFS are all done or managed through this magic .snap subdirectory. So we don't see it in a regular reader, but we can then just within that .snap directory. Create a snapshot. So now, yeah, we've, oops. One day I'll get used to that. So we now have, yeah, our instantaneous snapshot created within the file system.
If I look into .snap/mysnap, I would see the actual files in the directory.
Yes, yeah, you'll see the state, which currently hasn't changed. I mean, at this stage, we can do removal of this directory, and then obviously within the snapshot itself, we still see it. Also wanted to make a change to the file. Great. And from this state, I'll now then just show some of the integration we have with Samba. So this is work in progress. Yeah, we've just sort of pushed these patches upstream, so it hasn't all been merged yet. Again, it could all go up in flames, but we'll see what happens. Okay, so I have my Samba server VM already running, and somewhere here I have Windows. So hopefully, there we go. So we're just viewing the same file system I mentioned through the Samba Gateway. So this is a Windows Server 2019 client connected to this Samba Gateway. So within, yeah, I have a second screen here. We can see, yeah, we just have the state of that file after the snapshot. What we do have, so the integration I mentioned is that we have, yeah, this previous versions UI or functionality. So this is, yeah, sort of, I guess, a feature somewhat unique to Windows in that you have this ability to right-click on a file and then view the snapshots for that given file. Here we can see that we do have one corresponding snapshot with the file. Yeah, what happens here is that Windows basically just does a enumerate snapshots request to the Samba server at the back end, and from there we can look in the .snaps directory in Ceph or CephFS and see what exists. And yeah, we can also do things like restore and yeah, open from those snapshots. So basically, accessing snapshots, Windows clients add what's called a time warp token to these open requests, and that's what we again translate into a .snap path within Samba. Yeah. Anyway, that's all I had for the demo. Hopefully we can. Yeah. Rock solid. So now on to performance. Yeah.
Okay, let's do it.
Quick question. About the
Yes, sure.
Snapshots. Is that just at the top global mount point, or
No,
you can do subdirectories?
Is it just current working directory?
Test. Yeah. No, so within CephFS, basically subdirectories inherit snapshots from the parent. So basically, or for starters, you can create and remove snapshots at any layer within the directory tree. I'm not sure whether you can remove inherited snapshots. I guess not. But yeah, you can create them anywhere, and you have visibility of parent snapshots from the child subdirectories, and that's also what's utilized by Samba in this case.
Another question.
Yes?
Before accessing US SMB, you unmounted the CephFS native client.
I did.
Is that because of that multi-protocol access you mentioned?
So
that
So that's all we support at this stage with SES 5.5. I can say that on the roadmap for future releases is obviously exactly this feature. Yeah, in reality, you're only going to run into problems if you have applications which are accessing the same data set. Yeah, generally, I would say.
So right now you have to have different CephFS to access through Samba, and if you have native clients, you have to use a different one.
Sorry, I didn't quite understand.
No, I think you can. I mean, you can access the same directory via Samba and native, but you know there is no mechanism that prevents clients from both mechanisms stepping on each other.
So the main problem here is just locking at the Samba backend, basically.
The problem is that you have not consistent file locking.
Yes, that's right.
So
if you have
subdirectories and
so if you have applications which rely on locking within SMB or POSIX, then you may.
Or if you can tell all your Windows user to not use CephFS right now, then you can do whatever you want. You know.
But also in that regard, it is also possible to create snapshots remotely via Samba. So we worked on this with the SLES Snapper integration. Obviously it's still unreleased software, but we're also looking at in future adding that support to the CephFS backend for Samba too. And Martin, you had a question?
No, I just want to add that cross-protocol file locking is basically a feature we are missing at the moment.
Okay, performance. Yeah, I mentioned already, like some of these numbers are literally less than 20 minutes old, so we didn't have a whole lot of time to analyze them yet, but neither did we want to keep those numbers from you. And since we are already quite late, let's start. So feel free to look at that later. That's quite a dense slide. So we have quite a performant cluster with 8 nodes. It's flash only and 25 gig hard networking based. Our OSD nodes even have 100 gig NICs, which is obviously very nice for Ceph. So all I want to say is really a very, very performant cluster, and I'm just seeing an error. We only had 7 client nodes. Our OSDs are, as I said, all flash. In each OSD node, we have 2 pretty big NVMe drives and 5 SSD drives. Per NVMe drive, we deployed 5 OSDs. So the whole cluster, all in all, has 80 OSDs. And the rest is fairly standard. 3 months, 3 MDS, only 1 of them active, and a lot of RAM. Yeah, again, feel free to look at that later in more detail if you're interested. I just didn't want to leave it out.
I have only one question.
Yes.
I was there to mount to 68 megabits.
Yes. So it is quite low. I don't know how often you got to play with 100 gig networking yet, but it's very hard to squeeze the full performance out of it. Gigabits, yeah, sorry. What did I say, gigabytes?
No, it's megabits, yeah.
Another mistake, I'm sorry. Gigabits, yes. Okay. Sorry, but I still think it's quite low considering they are 100 gig links, right?
Okay.
It's, yeah.
It's quite better than megabits.
No, okay. That's, yes. I will change that in the online version. Right, 80 OSDs. So the workloads, since we didn't have a whole lot of time, we limited us quite a bit on the workloads. So we're running I/O from each client thread to 104 MB files. So each client has their own file set. We only got to do sequential I/O in 4K and 4 meg block size yet. To not run completely out of cache, we added fsync calls every 64 I/O operations. And we're running each experiment for 10 minutes with a 2-minute RAM time. And yeah, as I mentioned, 7 clients, not 9, with various process counts per client node. All right, so far, pretty obvious, right? Okay, first graph. The obvious one I want to point out is that really tall one there at the far end. Yeah, just that should be just under 15 gigabytes per second. The experiment that the workload that we were running was 4 megabyte sequential I/O from 64 processes per client. The last one is 128 processes, and you can see that they really start competing for CPU and cache there, so the bandwidth went down quite a bit. The 4K performance is, well, compared to earlier experiments, we had, I don't know if anybody saw the presentation in 2017 in Prague. The 4K performance is actually has improved, but obviously is still quite low, though it's surprisingly good, as we will see on the next slide. Yeah, and otherwise, there's some broad lessons to be learned here. Multi-threading is a good idea for CephFS clients to a degree, obviously, and we'll have some slides that point to why that is. Yeah, but you can squeeze quite a bit of performance out of CephFS. If we look at the I/O ops, with 64 worker threads in 4K sequential, we're just cracking the 1 million I/O ops. I think that's also quite nice. I'm also seeing that I haven't changed the legend up there. That should actually say 4K and 4M and not random and sequential. Yeah, I will change that. So if you look at it later, that should be changed. Yeah, with the 4 megabyte I/O ops, they're obviously nothing to look at. I do want to mention this is a log scale here. So otherwise you wouldn't see those 4 megabyte bars at all. And that's why it also seems that read and write are kind of skewed, but they're actually pretty similar. It's just due to the log scale that they look much smaller. And latencies, also nothing terribly surprising. Something went wrong with my colors here. The 4K latency, so this is a completion latency distribution. So we have the percentages of I/O ops on the Y scale, and X is the completion latency bucket. So the very far one down there is over 2 seconds. So you can see that the large block sizes with a lot of processes can take quite a while. And again, we'll have a slide that might point to an indication as to why. But if you run with 4K I/O operations and not too many threads, the latency can actually be quite snappy.
1 minute.
1 minute? Oh, we only have 1 minute? Oh, that's right. Okay, real quick. So this is an OSD node. The only thing I really want to point out here is that I'm coming over here. The disk utilization, so the SSD disks are almost 100% utilized during these experiments. The NVMEs, even with 5 OSDs, we're not even touching anything that maxes out there. This is from the client. For the really big block sizes and high thread counts, we just maxing out the CPU. It just keeps on waiting, and that's because they're massively competing for cache. More hardware will solve this. Oh, okay. No, but don't we have to make room for the next speaker?
We have 15 minutes after 3 o'clock.
Okay.
I was just trying to speed you up, but anyway.
Well, now it's your turn.
Yeah, so these are the Samba numbers we got. So again, they're hot off the cluster. We haven't had too much time to sort of analyze exactly what we're seeing, but I'll sort of try and walk through it. So again, we have just the 4K IOs on the left-hand side, and on the right-hand side, the 4 meg. I should, I guess, also give a bit of an overview of the Samba setup here. So in this cluster, I just deployed the Samba gateways on the OSDs. So we have 5 OSDs. I deployed a Samba Gateway on each, and each of those gateways was exporting an isolated subdirectory within CephFS. So I wasn't using CTDB or the scale-out functionality at this stage. On the client side, I was using the CephSKO kernel client with SLES 15SP1. So that's also pre-release code. We should also say this is this doesn't offer any reference for what will be seen in the field. This is sort of more just things we're looking at for in terms of finding bottlenecks on our setup. The CIFS or SMB numbers were also, I would say, better than expected in that we're also up around 12 gigabytes per second. We did see for the higher thread count quite a decrease in throughput. So Yarn was running at the top end with 64 threads and 128 threads per client. For the CIFS or SMB benchmarks, I reduced that to 16 and 32. The reason there, or at least from looking at it so far, it looks like we're seeing a bottleneck on the clients. So we only have 7 clients to play with, and it looks like we've got some lock contention in the CephSKO IO path. So I think hopefully if we start throwing more nodes at the cluster, we won't see this sort of tapering off, but otherwise still reasonably good results. IOPS were also just up over 1 million for the 4K workloads. Like Jan's benchmarks as well, I did have some client caching enabled, so it was doing an F-sync every 64 IOs on the client.
Yeah, the experiments are exactly the same, just different targets, really.
This is sort of the distribution. I think too interesting there. But, I think we can go to questions anyway. If anyone would like to know more about sort of the benchmark setup or numbers.
I know that multiple OSDs on really devices works better. Is that currently practice though in the field?
That is the upstream recommendation currently, because you've seen even with 5 OSDs, there's just nowhere getting near maxing out an NVMe. I didn't want to deploy even more because then they would get kind of silly size-wise. Even with an 800 gigabyte NVMe, running 5 on them, that's already less than 200 gigs per OSD. That's currently just a I/O path bottleneck that will hopefully eventually be addressed by the new C-Star project, the OSD rewrite, but that's that's going to be a while. Correct.
So it's now considered best practice.
If for standalone OSDs, yeah. Typically what you would do is probably use the NVMEs as WallDB volumes. We tested that very early on, but due to the very synthetic workload that we're running, we didn't see any I/O on Wall and DB, which is, partly due to the workload, partly due to the fact that the OSD machines have 128 gigabytes of RAM, I think. So it was just all cached. But in a more real-world cluster, you would benefit quite a bit from that. Yeah. In case anyone wants to grab the slides. So.
Is there any sort of rule of thumb or optimistic between your CephFS testing and your Samba testing? You could say there's a percentage of this much in it, or is that too early to tell, or are they reasonably the same?
It's too early to say. But 16 gigs versus 12 gigs per second, that's more than I would have expected. I don't know.
Yeah, I don't think that's a realistic expectation either, or at least that close a result from SMB, especially because generally we'd be deploying with CTDB2. In this case, I just had standalone SMB servers. Yeah.
Is the advice then there's definitely there's a performance solution in there, but test and find it?
Absolutely, yeah.
Hand it over there for a second.
Okay, can you tell us about something about the stability of the Samba Gateway? Did you incur crashes or random stuff you didn't expect?
I was testing with, as I said, our current development, internal development version, and there, no, I didn't experience any, at least on the Samba Gateway side, any issues. As mentioned on the CephFS, on the CephFS or SMB client side, we did run into a few issues with basically, socket timeouts on the client. There are some things to sort of tune and look at closer, and we'll be doing that in the coming days and weeks. So.
Just wondering about the single client performance. Any expectations?
So single client, single threaded, or I think. So the question was whether a single client with a single thread of I/O will still see a reasonable result. I think for Ceph, really that's one of the worst workloads possible. Ceph really sort of shows itself when you have a large workload connecting. Look,
we did run some experiments where we have the client writing to a single large file. I didn't put it in here, but this is this is aggregated over 7 clients, but 1 thread per client. Yeah. It's not too far from that. So with...
You divide that by 7?
Yeah, true. But, it's still a couple hundred megabytes per second. But we didn't optimize for that case at all. So I'm sure that can be better. And I don't know, for the Samba case, probably similar.
Yeah, look, there's a lot of tuning you could do with I/O sizes depending on what the client's sort of issuing, but
you mentioned several times that you have to clean up, flush the data out of the cache.
Yes.
To avoid a cache problem. Is that something that there is any plan to fix in this? A way to manage a cache in a more efficient way, that we don't have to manually flush it?
No, you don't have to. You don't have to. For a benchmark, we were kind of in the situation we could either just run with normal page caching, which we did in the beginning, or typically benchmarks are often run with direct I/O, and we kind of took the middle path here to have somewhat a realistic client caching behavior, but also make use of the cache that is there. So
Not to get better performance, but just to...
I would assume that actually hurt the performance a little bit. At least for the, not for the giant stack of the 14 gigabytes per second, but for the others, it's just synthetically inserted. So we used FIO for benchmarking, and every 64 I/O operations, it would do an fsync. That's not something that a typical application would do unnecessarily, Right.
Did you do any special tuning on the MDS side, or Samba side, or Ceph side?
So OS-wise, we enabled bulk MQ for the SSDs. We did a little bit of kernel buffer tuning for the networking, but that's mostly due to the really up-to-date networking hardware. It's just enlarging some networking buffers. On the MDS side, there was no change made, and for Samba?
For Samba, there was quite a bit, I guess, in that instead of using the libCephFS backend, we did use a kernel mount. So basically, with the next release, we plan on supporting both the BFS Ceph for Samba, as well as sharing atop a kernel mount. Yeah, so we had that as well as an increased AIO max threads. So just increasing the amount of concurrent I/O Sambas willing then to dispatch to the file system at the back end. We used the SMB 3.1 dialect, which I think anything basically above 2 should give you nice large I/Os and multi-credit stuff. So.
Okay, so just make sure with the release of the product that the defaults are set correct and we document them.
Look, we'll also be doing comparisons between the libCephFS backend and kernel.
And I think there was another question somewhere back there. Nope. Well, if there are no more questions then, thank you guys. And